Okay, it says curved arrows are used to illustrate the flow of electrons. Follow the arrows to predict the intermediate and the product of the reaction. Include all lone pairs. Use wedge and dash symbols to indicate the stereochemistry. Ignore inorganic byproducts. Okay, so we are actually given our intermediate, right? So if we're given our intermediate, and then they're also telling us that we're starting off with PBr2. I'm halfway blind, or PBr3, yeah. PBr3, I'm like, that's not right. And DMF, okay? So if we take a look at the PBr3, right? And our basically our intermediate. So what can we conclude about the starting product? Because that's what we're going to have to do. We're going to have to draw our starting product, right? It's an alkane. Okay. Are you sure? So an alkane, are you sure it's an alkane? Where would the oxygen come from? It was only an alkane. You drew an alkane? Start that out. What was the alkene that you drew? I'm curious. And again, where did the oxygen start from in that situation? Where's the oxygen coming from? Okay. Okay, so I'm saying you're not quite understanding what I'm saying here. Let me grab a. Okay, so this guy has an oxygen, right? This OH. We have this guy, right? So if we have this guy, you're saying that you're starting out with an alkane. An alkane would just be simply a hydrocarbon, right? Single bond hydrocarbon. Now, I believe that it's single bonded, but is it just a hydrocarbon? Because where are you getting your oxygen from in that case? Do you understand what I'm saying? So you're saying that you started out with an alkane, right? So let's go to the drawing structure. So these are your reagents. You're using the PBr3 and the DMF to sit there and cause this reaction. If you started out with an alkane, where did the oxygen come from? So did you start out with an alkane? You understand? Because an alkane is just hydrogen and carbons that are all single bonded, that are saturated, right? Okay, so did you actually start out with an alkane? Okay, again, if that's the case, where are you getting your oxygen from? Where's your oxygen coming from? So you're starting out with an alcohol. Okay. So that's the first thing that we want to establish, right? So one of the things that we're starting out with is that this has to be starting out with not an alkane. An alkane is just a in this case, it would be 1, 2, 3, 4, 5. So it would be pentane, right? Alkane is just that structure without the OH. Yes. So in that case, it would be 2-pentanol, right? So you're saying that you actually started out with 2-pentanol was our starting point, right? Was that? Okay. Oh, can I not? Okay, oops. One, two, three, four. 1, 2, 3, 4, and 5. Oops. Well, feel free to help your lowly instructor. Okay. What was that? What was that? That is a weird way of doing it because they're both on oxygen. Okay. Yeah.
I think we wasted most of our time trying to guess where the hell they're going.
Okay. That's good to know in the future. Yeah, but not quite, because lone pairs mean that they're dedicated to that atom. So they're constantly moving around that atom, oxygen. So it's not quite right, but because then we also know that oxygen is only going to be able to share 2 electrons. In that case, you're saying it's 4 electrons that are being shared. So, yeah, I'll complain about it later on. So. Okay, I know they get sick of me. I think everyone else does. Okay, so what was that? Yeah. Where is that? Oh, okay. Oh, thank you guys. See? Okay. The H.
You can have.
Okay.
But it helps for the next one.
For the very next one. Okay. Okay. So then, in this case, what's going to happen in this situation? So now we have, if we look at it, we have the bromine donating its electrons, because now we've taken the electrons that were generated here, provided it to here. The bromine now donates its electrons here. Then that causes the electrons to this bond to be donated here. So what's going to happen?
The OH is going to break off, right? Then it's just going to be bromine to that alkane.
Okay. So we're just going to get I can't say it. Halogenation. Thank you. I am struggling today. Oh, let's see. So then that's 2, 3, 4, 5. And now we have a bromine. So is it going to change positions, or is it going to be coming out towards us, or is it going to be going towards the left? Mhm. You put the dash wedge. Interesting. Am I forgetting anything? Yeah, I know why it's important. It's
Yeah.
just, okay. Says I got it wrong. Was that? First one's right.
Probably wants to.
It doesn't tell you.
I never seen that. It never seen that yet.
I got that.
Was that?
Like math.
It doesn't matter.
So you say it's this. What was that? Oh, that I put a method. My bad. A wedge. No, it won't work.
How would you know? See, that's what confused me. Legend.
I thought that bromine would have more priority over the hydrogen.
Mhm.
So I thought the bromine was going to have to be coming towards the other way.
It's not because the bromine has more as priority, it's how it's attacking the structure. So, and let's pay attention to that too, right? So here, in theory, we have that intermediate where the oxygen is being occupied there, right? So if the oxygen is being occupied at this position, this guy is taking the opportunity to go where that hydrogen once was, right? And so, and that's probably the reason why the orientation is the way it is, right? And so, and it does pay, it makes a difference, that orientation, obviously, we had it wrong. Because this guy's in the back, if we look at it, we have the hydrogen coming out front, we have a bromine up on the side, we have a methyl group on this side, and then we have a long chain on the other side. If we go the other way, it's going to be a different orientation, right? So it does matter in this case, that orientation. I said, so the bromine is going to be, in a sense, attacking from the back because it's providing its electrons before this guy is there. So the oxygen is already occupied in that position, right? By us adding the bromine has to attach first, right? So that means that it's kind of shifting that hydrogen that would normally be there, right? Because there's a hydrogen that exists here. Yeah, it's like, hey, move out of the way for a minute, right? Because I'm taking your spot. Yeah. And then after it does that, this oxygen, it donates the electrons to the bond. The bond then grabs this guy, right? And then if that's the case, right, we also had the fact that you're also going to get water formation, right? That hydrogen, but then the hydrogen has to come back. We still need part of that hydrogen, which we're not showing in this case. So it comes back and attaches later on. But that takes, was that, go ahead. No, it's taking the OH. Yeah, it's taking both the OH. So it's taking the OH, and so the bromine is coming here. It's affecting that bond right there. So it's donating here. Here are some electrons. Those electrons are then kicked out to the bond itself. The bond then puts the electrons around the OH. So then the OH has an OH minus associated with it, right? Which is going to initially first attract that hydrogen, which allows the bromine to successfully take its spot. So bromine is pushing that hydrogen to the side so that it can take its spot. So when you were drawing, because earlier Jesse had mentioned, he's like, well, there's also this hydrogen that's back here, right? The dash line. Okay, so that's valid, and the reason why we don't have to show it because it's a hydrogen, right? But we know that there's a hydrogen in the back. It's understood that way. This guy is pushing that guy in the back because it has to attach somewhere. So now you have that hydrogen still kind of attached, but when you mess with that bond, it kind of causes that hydrogen to have to shift, right? So it's pushing it like she suggested, it's bullying hydrogen to say, hey, I need a spot right now because I need a spot to kind of get this oxygen so it can move out of the way. And so then it allows for that change to occur. And so then it kicks hydrogen to the side and say, hey, you're to the side right now. I'm taking your spot. That allows these electrons to be transferred to the oxygen. And so in that case, technically you have an OH. Now that OH could also impact that hydrogen, right, temporarily. But at the end of the day, it needs to be stabilized. That structure needs to be stabilized so it gets that hydrogen back. So does that make sense? Okay. That's right. Yeah, that's right. And so if you think about it, bromine is strong, but oxygen is stronger, right? So if you think about the electronegativity that's associated with it. Now, so then bromine is taking advantage of that, the fact that you have that hydrogen, which is going to be weak in terms of electronegativity, and it's going to, okay, let me kick you to the side so that I can take your spot. And then I can adjust that hydrogen. Then I can adjust the bond itself, and then the oxygen is now released in that case. So we just get that hydroxide, which it wants in the first place, right? It wants to, ultimately reach its octet. Here, it's still able to reach its octet, and it doesn't have to share with the long mass chain. So it is a catalyst. Okay, and again, on that list, DMF, dimethyl formide, sorry. Yeah, and then dimethyl formide. Yeah, in most cases, it acts as a catalyst. There are occasions that it will actually, under the right circumstances, right conditions, it can use the amide of it, and the fact that it is a dimethyl. In most cases, it's just acting as a catalyst, just to kind of help that process. Okay, so but let's see. Okay. Oh wow, I got one right. Okay. Takes forever. Okay, so this guy is an epoxy, right? Epoxies aren't very stable. They like to sit there and donate. And so they're going to try to donate their electrons. Let's see, how do I say this? So when they get the opportunity to donate, but something always has to get them initially started, right? So in this case, we're using the hydronium ion to kind of get it started, okay? So the hydronium ion will then attach to our epoxy, right? So then this guy becomes a plus. Well, now you have water because the hydronium ion, that H plus, is attached here, causing this guy to be a plus. Okay, so then water has its electrons and it shares this electron. So what's going to happen in this case if it's going to donate its electrons here and then it causes this bond to be disrupted? What is going to be our product? Okay, so you have this ring structure, right? Oxygen is here. So what you've done, you're having this bond be disrupted. So what's going to happen to that ring structure if that bond is going to be disrupted? It's going to open up, right? So then we're going to basically get this, that. Okay, so then, let's see, right? And then we have lone pairs. Man, I'm going to be in so much trouble in this class, aren't I? How long did it take you guys to realize that you needed the lone pairs too? Okay, so that's 1, 2, 3, 4. Okay. Okay. So mhm. So it's donating to this first carbon, right? And carbon isn't happy because it's like, okay, I'm kind of cool where I'm at. So it causes this bond to be disrupted and it donates the electrons to here, right? So then it goes from negative, right, to, I'm sorry, it'll go from a positive to a negative value, which causes it to be balanced out, right? So. Okay. So. From there, do it again. Okay, and then. Okay, so then what's going to happen when we do the neutralization work then? The oxygen is going to donate the hydrogen. Okay, so we're going to get 1, 2, 3, and then double bond. Oops. Sorry. You're making fun of me. Put the what? Yeah. The water, the H2O. It would actually be connected at this point. You're right. Okay, so what is the secret? Where is the H2O?
Just connect similar branches, carbon, oxygen. No, for the top.
Right here?
Yeah, connect them one, and then convert those to hydrogen.
Okay.
And then,
Which is the third one.
no, the other one.
Arson.
Okay.
Still need our lone pair.
Yeah, it's like lone pair and then charging.
You guys are asking for too much stuff.
That's what we tell them every time.
Yeah. Okay. what did I just do? Undo. Okay, lone pair.
Third row, second.
Okay, did I screw up? Yeah. And that's 1, 2, 3. 4. Okay. What did I forget?
There's 2 OHs. I believe, yeah.
Oh, it becomes a,
Yeah, because you have more. Actually, I forgot how I did it.
Yeah, and then
okay, let me get the lone pairs. Oh, no, wrong way. There we go. Okay. OH. Oops. No, that's. Okay. Yeah, it's gonna take me a minute. Okay. So why don't you get the keto aspect of it? And why is it just the OH?
Because I mean it's gonna turn neutral, so you have to get rid of that cation.
Okay,
But I forget exactly how you do it.
okay.
Oh, I think the hydrogen breaks off and it gives the electrons to
It
the
donates.
O.
Okay. Yeah, so when the hydrogen, so we end up with the H plus, which is going to reformate because it's in a aqueous solution. It's going to reformate the hydronium ion. And then this guy is, in that sense, going to be giving up its electrons. This bond allows that hydrogen to give up its electrons to make the OH more stable. So what is it that's going to cause that keto or the, what is it? Telomeration? Not telomeration. Yes. Tatra. Is it Tatra? Telomeration. TAUM. Yes. Tautomerization. There we go. Tautomerization. I think we're adding too many vowels there, right? So, but basically, we're going to be going from an alcohol to a ketone. That's what you were suggesting earlier, right? So, what is it that causes that to happen? You guys recall? So, do me a favor. Take a look at your. Do you guys have your list of Leah for psi? Yes, the ketone formation, because it, yes. But you also have, in this case, you have an acid catalyst, right? Because the OH is going to be acting in that sense. But you're talking about in the case of mercury, the mercury sulfate and the sulfuric acid. Yeah. So, and in that case, you're going to get the enol form first, and then that's going to cause that double bonding to occur, right? So if it was a double bond here at some point, say in this situation, there's double bonded there, then that would cause that formation, right? So I think it's a alkaline alkyne reactions. It's on hydration. Let's see, right there. Okay, so let's go to the next one. Since I got it right. Now we're doing more curves, right? More where the arrow is going. That's one that we just did. Did you guys finish this homework assignment already? Most of you? Okay, what am I doing wrong? Didn't I press 4? I've been having this week, nothing has liked me. I've been having so many issues with programs. Oh, there we go. Okay, so another epoxy, right? So what's going to happen in this context? So we know that in this case, our electrons are going to be donated by the organometal. Yeah. Would it make it positively charged?
I think the oxygen negative, isn't it?
The oxygen should be negatively charged. Okay, so that would be our intermediate. Is there a quick way to draw ring structures? It'll allow me to scroll down. Okay, there we go. Okay. So then, so what's going to happen in this case?
I think the methyl attaches to it, doesn't it?
Okay. And then that means that this guy is it's going to cause the disruption of this bond. Right. And so you're going to get an opening up of your, right, oops. What was that? You only have an OH.
So just click on the OH. The charges and compare.
Oh, I see it. Okay. So is it not? Right here? Okay. Okay. Anything else gonna happen? Anything else gonna be attached? So is it gonna be attached to the oxygen? Or is it gonna be attached to the? What was that? How do we get which carbon? This one here?
Yeah.
From the methyl. The methane. right here. I'm asking, are you guys disregarding the magnesium bromide, or is the magnesium bromide still going to be attached? Okay. Yeah. No. Maybe. Okay, so what do we know? So if we have the magnesium bromide, so we know that this guy's being attached by a negative charge, right? So, and this guy is going to be a positive charge. That's what's causing that interaction. Okay. So when we transfer these electrons, right, this guy has a negative charge associated. Right? So, what was that? So it's going to want to attach itself to so is it going to want to attach itself here? So should we have a magnesium at the end of our carbon structure? Or should we have magnesium that's going to be attached at this level? Above? Okay. I'm going to do that. I don't know, but we'll put it down there, right? This guy, right? Was that? So you're saying that the magnesium should be attached here,
Yeah.
and then that carbon should be attached here. Is that what you're saying? Okay. Yes, we are supposed to be looking at the ether, but what's going to happen to our structure? So you're saying that the ether is also going to be adding carbons. Is that what you're telling me? And where are they going to be adding carbons? to the oxygen? Okay. So you're saying the ether is going to be attached. Let's see, 1, 2, and then we have technically would be, is the whole ether going to be attached? No. I said, is the whole ether going to be attached? Because this is diethyl ether, right? True or no, right? Diethyl ether. Okay, so we have diethyl ether, and you guys are saying that the ether is going to attach to the oxygen. So how's that going to work for me, right? So basically what we've done, we disrupted this bond here, right? And added the electrons here. So that means that this guy is going to be attached at this level. So the question is how is this guy going to be attached? That's my first question. To this structure. I mean, to this point, because this is the epoxy. The epoxy, the bond between the oxygen and this carbon is being disrupted by this compound, right? Okay, so you're saying that in this case, this guy is going to be a cation, so it's going to be a plus. No. Keep saying on the cyclohexane. Looking for my epoxy here. Give me a second. This one is a challenging one, right? Epoxy makes it hard. So we know that there's the last time when we donated the electrons, right? The water actually attached to the structure. That was our intermediate, right? So in this case, one thing we're not getting. So, and we also have diethyl ether here as well. So the diethyl ether, you guys are saying it's going to react with the oxygen. Is that my understanding? Section. Okay, do me a favor. Do you guys have your cards with you? Let's see. Okay. Look for epoxies. Somebody saying something? Yes. Did you guys see a reaction with the epoxies? It's yeah. Yeah. 85, 91. The 85 is the formation of epoxies. Here we want to use epoxy as a reactant. And my cards are all screwed up. 88. And 90. What did I say? That's the condition. Liquefy. Get a nuclear file attached. Which separates forming the OH. Basic conditions. 92. So 90, yeah, 92. If you take a look at 92, we got. Okay. Yeah. But how did you get that?
Was it just
Yeah.
to just like drag it out of the machine?
No. So I think the diethyl ether is just acting as a carrier in this case. So it's not reacting in the reaction. So let me. So which is what initially what you take a look.
Yeah. Either click on
Okay, so but do me a favor. Can I see you said it was 80, 98, 99, 90, 92. I have it here. See if I can find it. 92. Pull it up. Because if we take a look at that, right? 92. So it's just the opening of an epoxy, right? And so if it's under acid conditions, then we get the nucleophile added here, we get the epoxy here. If it's under basic conditions, we get the nucleophile added on the opposite side, and then we get the OH. So in this case, we have the nucleophile being added here, right? So, and then after it's worked up, then what are we going to end up with? Negatively charged. Actually, same. So cis instead of trans. Trans instead of cis. Okay.
bonds, right? Not gonna create any double bonds.
Right now, we're not creating any double bonds. Yes.
So would that be-
No, there shouldn't be any double bonds. So after neutralization, this is, so we're just basically going to have water present so that we can actually have the neutralization occur. So then what's going to happen to that the oxygen, the negatively charged oxygen? What was that? It becomes an alcohol. So is there any way that I can copy this? Okay. Because it's being neutralized, because we're getting rid of the negative charge, right? And so we wanted to have it so that it has a stable charge or a positive. So it's going to use the water to sit there and from water. It's going to be added from water. Yeah, so in this reaction, so it looks like we have diethyl ether, right? And make sure I'm not. We'll get the methyl group added on. That's going to cause that split. So this allows the methyl to be added on. Then we get the negative charge onto the oxygen. And then it just says, what was that? It's just a carrier. It's acting as a carrier. And then it says neutralization workup. So that part means that you're going to just neutralize it, right? So in this case, if it's a negatively charged, right, then we're going to add some, because if it's negatively charged, we're going to add a little bit of acid to neutralize it, right? Yeah, so the ether is not going to attach. Yeah, so that, okay, for instance, right? So we often will use ether as a carrier for certain substrates, right? Now, don't get me wrong, ether can react with certain things. But typically when ether is involved in a reaction, that is, you're going to have a thermal type of component added onto it to kind of initiate that. Okay.
Like magnesium bromide.
No, because the magnesium bromide, so right now, this is attached, this is guys being attached because of, okay, so if we have magnesium bromide, we have one bromide. What is the charge on magnesium? It's positive, right? Okay, so positive what? Positive 1, positive 2. It's positive 2, right? Because magnesium is group 2 metal, right? So this magnesium, this bromine is adding only its negative electron. So then in this case, this guy is also providing a negative electron, right? So then that's the reason why we're able to sit there and get this to happen, because now our carbon has a negative charge associated with it. Does that make sense? Because you remember when I said, okay, so who's going to be donating electrons? Right? And then Mauricio says, well, if it's negatively charged, or if you have a carbon, which is normally like neutrally charged, or it's going to be positively charged, if it's negatively charged, that's going to be our donor. So here we have a negatively charged carbon, right? And so this guy is going to be donating its electrons to disrupt this bond. And then once this bond is disrupted, then it's going to carry on. The magnesium bromide would not be, oh, you're asking, yeah, in a sense, it would have a plus charge associated with it, right? Because you have this guy now is going to be Mg Br plus, because you no longer have the chlorine and the electrons that the methyl group, and you no longer have the methyl group that is providing that negative electron. Those electrons are being provided here, right? Why is this guy there? It does, and because you want to think that it's reacting, but I think the purpose of it is so that we get used to seeing the reactions with the carriers so that you don't misinterpret what it does. The hydrogen is from the neutralization. When you neutralize something, you're going to either add acid or you're going to add base to neutralize it, right? So if it has a negative charge in our intermediate, what are you going to add to neutralize it? Water can do it. A lot of water can do it, but all you're doing in that case is that you're removing the H plus from the water, right? So if you're going to neutralize something, let's say I spill acid on the floor, right? What am I going to use to neutralize the acid I spill on the floor? What was that? I'm going to use a base, right? And then if I have something that is negatively charged, chances are that is going to be an acid or is that going to be a base? What was that? No, this isn't acting as a neutralizer. When it says neutralizing workup, that just means that we're going to add whatever needs to use to neutralize it. It's not telling you so that it's trying not to give you the answer without giving you the answer. Does that make sense?
And that way there'll be an extra oxygen, and then that's where it has to stop to.
Okay.
But
Well, this here, right? This would be our quote inorganic byproduct, right? So, but we know that this guy is going to be produced because we know that here we only have one bromine that's attached to it, so it's not totally neutralized. We know that the bromine is adding that one electron that it likes to share. So then we know that Mg is always going to be 2 plus, so that means that we have an extra electron on our methyl group, right? So in that case, we have CH3 with an additional electron, right? So that means that you have that pair, a lone pair of electrons that you could actually provide, transfer over, right? Because carbon has how many valence electrons? 4. Carbon has 4, and the hydrogens are offering 3. So then that gives us a total of 8. So then we'd have basically a lone pair that's here that we can sit there and I should put a minus that we can kick to get this guy started. So it uses those extra electrons to get that guy started. This guy is just going to be a byproduct, right? It's not going to react with this guy down here. Okay. And then once we get the ether is just going to be carrying the methyl group, right? And that's it. It's just acting as a carrier because ether kind of has a nice characteristic about it that it has that oxygen on it, right? And it has the carbon chains on it. So you can put things that may have polarity in it and it will actually be suspended in that, such as something like that. And you can also put things that don't have much polarity in it, something like this. Right? So, and again, I think this here is used to trick us, right? And so if you see ether, right, unless ether is being heated or sunlight, or then it's not going to be a component of the reaction. It's being used as a carrier. Okay. So So particularly in these questions, right? Because they wanted to try to get you guys to think about the reaction. And this one is kind of a tricky. And if you guys can do me a favor, kind of write this reaction down, because if you have this is an example of a organic metal, right? Or organometallic metallic compound. So this is an organometallic compound, and write it down. So if we have an epoxy with an organic what are going to be the products, right? So write a card so that you'll remember it. Because I think this is the part of the problem, is that we get introduced to these reactions so quick, and in the chapter it's not clear, okay, you need to remember this reaction. So what we need to do is we need to start going through the notes and say, okay, these are the reactions that we got from it. And this is an example of a generic reaction. So if I have a carbon chain that's 8 carbon long and it has MgBr at the end, what's going to happen when I add it to this compound? When I add it to this epoxy? Yeah, so if it was an 8 long carbon chain, it's going to break again. You're using its end to attach itself here. So it's going to break this bond, and then that means that you have the oxygen hanging out here. Let me actually use the damn program since I'm pushing it. So oops, wrong thing. Okay, and I want to put oxygen. If I press this, what? Yeah, change where I want to be. Oops, no, that's not what I wanted. Undo. I feel so inept. What was that? I need to use this one. Okay, and then I just use, okay. So, and it has dots, charges. Okay, so on this, and let me fix that. Okay. This here, right? So if this was an 8 carbon chain, then this guy would be an 8 carbon chain that's just added onto it. So generically, if we write it down, can I write it on the board? Or if I write it on the board, will you guys be able to see it, Abby and Kayla?
Yes.
What's that? Yeah, so it would take, so if this was an 8 carbon chain, it would take the whole chain because it's attached to it, right? So literally all you're doing, you're saying that R, Mg, MgBr plus epoxy and it could be just a general epoxy, or it could be a ring structure epoxy. I'm not going to draw that. What's going to happen is that you're going to get, and then we'll say, ethyl ether. E. We're going to get opening of that ring structure. So we'll get R. And then plus. In this case, it's going to be, if this is a negative charge, so this is going to be an acid, H3O plus added onto it. Can you see that, Abby?
Yeah.
Okay. So this is what's happening generically. So if you make a card of that, right? So, and all you're doing is you're disrupting the epoxy. You're breaking the epoxy ring and you're forming the OH, right? And so if you take a look at 90, just had it, not 93, 92, right? Where's 92? This is a D. I was being di ethyl ether. Being lazy. I don't think it's on our abbreviation. Or they often say just ether, right? Ah, there we go. Okay, so if I got it right or did I get it wrong? Oops, forgot. Changing orientation. Oops.
So why is that whole dash?
Okay, so again, the oxygen is front, right? So the oxygen is coming towards us. So if this guy's going to be attaching itself to kind of get everything started, it has to attach towards the back, right? So because the front is being occupied. And again, oxygen is stronger, so it can't kick oxygen to the side. So it's going to come in towards the back. So it's attacking towards the back. So it's going to be attaching towards the back.
No, I don't. So is that what it's saying?
Yeah, so in this case, we have, yes, we have the oxygen. There technically is a hydrogen that will be coming off the back. So then it's going to be taking a hydrogen right there. And then it's going to be giving the electrons over. Okay, then that separates our bond. So then we get the opening of this, but it's in the back now. So now that the oxygen has been released, because the oxygen is in front, right? It had to attach here first, right? And then oxygen is going to remain in front because it was in front initially. And then we do the neutralization. Okay, does that make sense, sort of?
Yeah.
So if the oxygen is in front, it's going to be come towards the back. So depending on the element, so if the element that's donating the electrons is forward already, then it's going to have to go, I mean, if the element that is receiving the electrons is forward already, it's going to have to go in the back. that's right. Let's see. Can I erase all my gobbledygoo? We'll figure it out. Okay, so let's see. Let's do next question. Yes, my computer is not liking Chem101 right now. Okay, so this is our intermediate. They want us to figure out what our reactant is. What are we starting it out? Starting ether. So obviously we know that it's an ether. So what is going to be our starting ether? What do you guys think? Okay, perhaps the same one that's being shown as intermediate. So you're saying basically this ether. Okay. Oops. I'll get the hang of it. It'll take me all day, but I'll get the hang of it. There we go. Okay, isn't that our ether? Lone pair. Okay. Yeah, I probably use up all my attempts on lone pairs. Okay. Okay, so I believe that's the starting ether. You guys agree? Okay, so then we know what's going to happen. Who's going to be donating electrons in this case? Who's going to be donating carbons to oxygen? Think about electrons. Where are the electrons going to be coming from in this case? Is it going to be coming from the bromide? But how do you get to the bromide? How do we separate that? Look where the plus is at. Off of the oxygen, off of the what? Which molecule is it coming from? Oxygen off of what? You're saying it's coming off of the oxygen. What was that? The ether, is that what you're saying? The ether is donating its electrons to the hydrogen, right? So then that causes the hydrogen. There you go. It brings the electrons over here. So then we get bromine minus. This guy becomes plus. It gets stuck to the, okay? So it's going to be our product. Come on. So now we got the electrons being donated here. Goes here. What's going to happen here? Okay. Okay, so we have these electrons being donated. And then this guy is going to do what? Donate those electrons, which causes this guy to what? What's that? Give it to the electrons to oxygen. So then oxygen, we have this. Let's see. Don't forget its lone pairs, right? Okay, lone pairs. That work? Okay. Anything else? So then we end up with just an alkaline halide, right? As our byproduct. Do they make you draw? You don't have to draw. So I hit done. And I'm probably going to get in trouble for doing that one's common sense. Okay, our next one. Let's see if Chem101 lets us. Is yours responding so slow? Or is it just my computer? Okay, we have an epoxy. What's going to happen? Acid conditions or basic conditions? We're adding arrows, right? So who's going to be donating? Who's the donor? So you're saying oxygen is the donor. Okay. Okay, do I just hit the arrow again? Okay. This isn't that bad. Oh, do I hit done? Oh, look at this. I am on a roll today. Okay. Oops. Okay, so we get that plus. What's going to happen now? I need to select that. Draw my arrow. This guy. Okay. And then this guy. Anything else? Yep.
Why didn't bromide attack, the other? I mean, bromide didn't attack.
Why you're saying why wouldn't it attack this edge?
Yeah.
I guess. Well, the alcohol, well, yes, the alcohol wants to be at the end, but if we, okay, so if we take a look at this, right? You also have this group right here, this chain right here. So it's always going to, it's going to attack the point where that chain is connected. So you have this here, that chain, and that chain. Where in this case, it has 1, 2, 3 attached. Okay, this guy has 1 attachment, so this is favorable for that bromine to attack. Right, and it's also favorable for that bromine to attack because that triangle structure is unstable, and primarily at that point because you have 3 attachments. And that's it. Okay, so I just have to hit submit if I can find it. Did I get something wrong? Can't see it. What was that? Okay, 7. Man, it is struggling. So is it always this slow or is it on occasion? Is it more so recently? Because like I said, a company just bought them. And so they keep saying, oh, nothing's gonna change.
They
Probably. He complains all the time. He always sends us messages. They probably didn't tell him about me yet. Mauricio, how's it going? they're called active. Yes. Yeah, they also bought, they bought two of the, like two, one of the kit making companies. Yeah, that we had bought kits from. What was that? They did? Yeah, but I know that they were talking about that. It was in their newsletter. How are you guys doing at home, Abby? Can you guys see my screen still?
Yes.
Okay, number 7. Hi, do you need to get in?
Yeah, I was like, I wanted to get the, like, I mean, I say, yeah, and I'm that from lost, and I'm like, oh, yeah, like, it's good, but like,
What about that 5-1?
well, I grab up on it, have to get rent, so like, the 20 feet for the price, I don't have that on mine, really, yeah. So, there's some deals that other people have.
I know. I'm gonna get too happy. I was like, what the?
Like now,
Yeah.
wait, how is it? Oh. I only say that because there's more processing than you write it. Got to, but you know. Really? Oh, did they cancel 2020? Yeah. 2020. Maybe already got like pushed really far back. They did. Really? Really? Go down in front of the hair.
I freaked her the hell
Oh,
out.
and the people that did in school, like, no. And the people that said it was were like,
They're all freaking out. I'm just like.
you guys recording? There's pictures.
Okay, who's the donor?
What'd you say? I'm just like,
Yeah, she was processing and then she saw the next one.
later, but like.
That's it.
What's gonna happen? Gonna donate to. Oh, they don't do. We got ahead of ourselves. Oops. Cancel.
So when the Austin is gonna donate.
So this carbon. Okay. That's the arrow. Yes. Mike is not working. Does it crash? Okay. So you guys get used to moving the arrows, right? No problem. Number 9. Okay. How are we doing on time? We got a few minutes, yeah. 5:14, we're doing good. So we'll do number 8 and then we'll do number 9. You guys, you don't need number 8? Okay. Oh, I forget you guys are in group chat. Okay. So. Something. Remind me, I need to bring cover slips and microscope slides to Fireball. Okay, let's see. Oh, this is a good one. What was that? Okay, let's see what our product is going to be. Who's going to be the donor? That is correct, because aluminum doesn't want to have a negative charge, right? Okay. So let's see. Arrow. And then who is it going to be donating to? The carbon with the most hydrogens. This one right here? Right here. This carbon right here. Okay, because that's. Are you sure it's not this carbon here? This has 4. So you say it'll go here. Well, we can also kind of take a look at our product, right? So shows to break it here, it looks like. So, doesn't matter. Whoops, no. Undo. Undo. How do I do that again? What was that? Oops, sorry. Okay. So you got it? Okay. Now you get a hit. Submit.
It's like where it gives you the arrow, like leading to the next product, and I put like the audio line right there, right before that.
Yeah, you're like, where the hell did that come from?
Yeah, I was like, where's that?
Yeah.
Like, if you messed up, and you'd be like, wait a minute, how the hell did
Yeah. Where did this guy come from? I get it. Okay, which number? Is that it? 12 and 13? You said 12, 13, 17, and 20. You guys have? Okay. Oh. It's pain without the S.
Same without the S.
Um, No, actually, I don't. Compared to normally, I would have 50. But okay, let's see if it's got to work. Let me see. Somebody said something. 13, 17. It looks like I need to update again. I just updated last week, though. It's Russia. So 13, you guys, 12, 13, 12, or just 13? 12, 13, okay. Okay. Oh, cool. Gives us choices. Okay, so what's going to get me from here to here, and from here to here? So excess or equivalent? Okay. Okay, and then what is going to get us to our intermediate? And ultimately here. So if we work backwards, so what's happening here? We're adding more carbon. So what process added more carbon? Just look at this when we're working with triple bonds. An alkane and halide. Let's see. Alkane and halide. Okay. Any other thing? So an alkane and halide is going to give us okay, the addition. So you're saying go here. Which one of these? So we have an alkane. We have an alkane halide. How many carbons are we adding? 2, 3, 4. So 1, 2, 3, 4. 1, 2, 3, 4. This guy's a double bond. 1, 2, 3, 4. They all have 4. Okay. So an alkane halide. You're saying D or E? Okay. And why do you say it's E, not D? Okay. Okay. Uh-huh. Okay. And then the order that is also being done, right? Okay. Okay. And so like that. Okay, so then when this happens, we get Okay. And I got my the OH. Charges. It doesn't ask for lone pairs. Okay. And then what's going to get us here? From here to here. This one? Or A or B? B? And what's going to be the difference between B and D? System trends. Yep. See if that's right. I believe so. Is it crashing on you guys too? So it's not just me. It's just really slow. That was pretty fast. 13. Predict the missing reagents and or products needed to complete the following synthesis. Tab. So, what do you guys think it's going to be? Which ones that we know we can eliminate? Which one? We're going to eliminate B, right? We can eliminate C. And we can eliminate E. So it's going to either be A or D. Which one do you guys think? D as in donkey? Okay. Okay, so let's see if we can, you say D as in donkey? Okay. You said A, so we got 50-50. What do you think, Israel? You say A? We'll go with consensus. Because right now it looks like both of them fit, right? But what? You said D? Okay, so let's talk about it. Okay. So we got like 50-50. This is an interesting class. Okay, so who's attached? Okay, so we have NO2 that's going to be attached, right? And what was that? You're thinking to yourself. Now, if we have sulfuric acid and we have it, if we take a look at this, this is just straight sulfuric acid. This here, sulfuric acid. So basically you're adding just a little bit to catalyze. In another case, you're adding a lot. So in that case, this here, you have nitric acid and sulfuric acid that's acting as a catalyst. Here you're adding nitrite, which is going to be like a base, and a lot of the acid. So what do you think is going to happen in that context? What's that? They're going to neutralize each other? Sort of, yeah, that's part of it, but also you have so much of that sulfuric acid that you're going to end up getting a thio added on there instead of a nitrite added on. In this case, you're adding so little, and then also it's an acidic reaction. Okay, so we're trying to add the nitrogen to the structure, right? And not nitrogen and sulfur to the structure. So I would say it's going to be A. That would be my guess. That's right. If they said cat, HSO4, you would still have some issues because this is a basic reaction. Then that means that you're gonna, I mean, it's basic in that context because you only just have a little bit there. And so that would probably be neutralized by that. Okay. That's what I think. Okay, so then what are we going to get? It's going to be an intermediate. Don't tell me what to do. I'm going to see if I can get it on my own. And I feel like a little kid. If I can get it to behave. This one. And we have, oops, no, that's not what I wanted. Yes. Okay. Yeah. Okay. Okay. So then we have if I choose this, will it? Oh, I did. Okay, so I need to do this. This one. And then was that? Okay, what did I do? Okay, double bond it here. Okay, so what's going to be our intermediate? I mean, what's going to be, so what are we going to get after the 10 chloride added? Okay, so you're saying this oxygen is going to be donating to this. And this is going to be donating to. Okay. So if we think about it, right? Can I erase? What you're saying is that this oxygen is going to be donating to, because it has electrons, it's going to be donating to HCl, right? So what's going to happen when we donate to the HCl? Then the hydrogen is gonna, okay? So then we're gonna end up with and I should probably say we have quite a bit of this 10 hydrochloric. This one we haven't gone over yet. We haven't really gone over amide, so you guys are kind of disadvantaged here. So what's going to happen is that you're going to end up with just this guy. I'm going to go ahead and give it to you since we're tight on time, and then also we is it? Oops, no, that's not what I wanted. Oh, not this. There you go. Want that line. There you go. Okay, and then C. D. No. And the final product. Was that? Which part?
The one with the SS1.
This one here.
Yeah, there's another option with only two carbons. Sorry.
1, 2. Okay. Yes, you're correct. Did I put? Yeah, you're correct. Okay. And what's going to happen next? We're adding an acid. Again, I'll give it to you since we haven't really talked about the amides yet. So it's my bad. maybe. I may give it to you if I can get it to move. Getting better. All right. Yeah, at the bottom in H2. It forms a carboxylic acid. So this part forms a carboxylic acid, and then it just donates that hydrogen to the nitrogen to give it, yeah. Okay, 17. Let's see if or do you guys want to do 20? 17 or 20, one or the other. That's the ones that you guys hit, right? 17 or 20. Is that the multi-aligned one? Okay. So what's going to happen here? We saw this earlier. Okay. So DMF is going to be a catalyst, so we're not going to worry about that. But the phosphorus bromide, tribromide is going to be our beast, right? So we're going to get, okay. And then we're going to get, where's it going to attach? But also, let's look at it. So we're going to get a final product. The final product is going to be what? What happened the last time that we used the PB3? The very first step was to do what? It broke the epoxy, and it also added what? Bromide. Okay, so it's going to be adding bromide and replacing the OH, right? So let's see. Okay. Okay, now we're adding a strong base, basic conditions, and heat. So if we have a halide, we add a strong base and heat to it, what happens? An alkaline halide. Talked about this earlier. We were talking about the formation of alkenes. Strong base. Halide. There's a handout I gave you guys. So for a strong base and an alkaline halide, then what was that? Dissociate. We're going to get the formation of the double bond, right? So the double bond is going to occur here. And again, this was like towards the end of last semester, which you guys are like looking at me like that's crazy most of the time. So if I click on it here, what is that? Oh. Okay, stop making fun of me there. There we go. Double bond. And then this guy. Here. Okay. That's right. And it's because the bromide, it's going to be basically you're removing the bromide with the combination of the strong base and heat. Okay. That's right. So it's just going to pluck this guy and then it's going to cause the electrons to move to here and get that formation. Okay. And this was the first chapter when we looked at the epoxies. We ran out of time. Not the first chapter, it was the 5th chapter, I believe. We ran out of time at the very end when we were talking about epoxies. So we get the formation. Oops, sorry. Okay, how about I extend those 2 problems? You guys have 17 and 2 left to do. I'll just add those to the next homework assignment, and then we'll have you guys do them then. Okay, I'll see you guys